Swayam Prabha. Digital India. Educated India.
Let us consider another example to clarify some of the basic concepts which we have been considering on this chapter. For instance, there is a structure shown to you on the screen. Let us draw the conventional unit cell and also the smallest unit cell for the structure. What is the lattice parameter for the structure and what is the motif? We shall also try to calculate the number of lattice points per cell and also draw the shortest lattice translation vector. As you can look at the structure, it has got two large circles which are white colored. There are two grey colored circles, one of them dark grey, the other one light grey, and they form a pattern which looks very beautiful in 2 dimensions. Now, I need to identify the lattice points before I can start to draw lattice translation vectors or the unit cell. Let us look at two circles which look identical, at least in form, but we will try to identify if they both qualify to be lattice points or not. So let us consider A and B as the two circles. If I look at A, then at a certain distance, of course by going along X and then coming along Y direction, I land up at a dark grey circle. If I do the same translation operation as shown by this red vector, I land up on a light grey circle. This implies A and B do not have identical surrounding. That means A and B both cannot be simultaneously lattice points. So now, for my choice, let me go ahead and choose A as a lattice point. That means all the A's would form a lattice. This point, this point, this point. Equivalently, I could choose B as the origin and the set of B's would also form a lattice point. But the point to be noted is that A and B both simultaneously cannot be lattice points because of their environments being different. Now let us overlay the unit cells, the shortest lattice translation vector and the motif which will go on to generate this crystal. Now, as you can see, if I join the 4 corners made of A kind of circles, then I can get a blue unit cell which is also happens to be the smallest unit cell. However, I can go and choose an alternate unit cell as shown by the green colored outline, which also happens to be the smallest size unit cell. How do we know it is the smallest size unit cell? Of course, I can calculate the area and find out that both of them have the same area. There is another possibility. Let me calculate the number of lattice points in this blue cell. Each one of these corners contribute 1/4 and therefore the net contribution to this is 1 lattice point per cell. Similarly, since these two circles do not belong to lattice points which are of the B type, only the corners contribute and the net contribution from these corners to the green unit cell is again 1, which tells you that it is the primitive unit cell. So if you were to choose a conventional unit cell, you would actually go and choose the blue unit cell. Now what is the shortest lattice translation vector? The shortest lattice translation vector in this case is the one which connects the A position to another A position as shown by the red colored translation vector. Of course, I could have also chosen the equivalent one, which is the one connecting an A position along the Y direction to another A position. So both of them will be the shortest lattice translation vectors. This obviously, the vector connecting this A atom to the B atom is not a lattice translation vector. That point has to be noted. Mr. Debtosh has a question for us.
What is the difference between conventional and shortest unit cells?
You mean the smallest unit cell. So question of Mr. Debtosh is, what is the difference between a conventional and the smallest unit cell? This point we had considered in somewhat detail before, that we used 3 criteria when we go ahead and make a choice of a unit cell. Number 1 being the symmetry. So we choose a unit cell which has symmetry commensurate with that of the lattice and the highest possible symmetry. Number two, if there are two unit cells having the same symmetry, then I would choose a unit cell which has the smaller size. But if both of these fail to resolve the issue, then I would choose an unit cell which is guided by some kind of a convention. Maybe we will consider an example later on in which we will see that even this convention is not without some kind of a common sense logic. Now in this case, the blue versus the green is the choice which we are trying to make. It is clear. Of course, again to reiterate the important fact, we are not talking about just the symmetry of the lattice, we are independently considering the symmetry of the unit cell also. So the symmetry of obviously the square unit cell is higher compared to the symmetry of the parallelogram shaped unit cell, because the square unit cell will have a fourfold symmetry in the center. It additionally would have those mirrors which we have seen, and therefore my preferred unit cell for this, which is also the conventional unit cell, is the square unit cell. So now let me find out what is the motif for this structure, which I need to put at each lattice point so that I can generate the entire structure. The motif happens to consists of two open circles, the A and the B circles as I had labeled them before. It consists of four dark grey circles which are filled dark grey and four light grey circles which have been put within this red dotted line and shaded yellow for better visibility. So this is my motif which goes and sits at each lattice point to generate this crystal structure which is shown in the figure. Now what is the lattice of this structure? It is a primitive square lattice. And what is the number of lattice points per cell? Since it's a primitive lattice, it has got one lattice point per cell. Okay. So this example again brings out the importance of the lattice and also the motif and the ways we can choose a unit cell and also the shortest lattice translation vector. Now it is time for us to go and consider 3D lattices. So far we have been dealing with one-dimensional and two-dimensional lattices. Now let us consider some three-dimensional lattices, and we shall try to study their properties as well. Now, to generate a lattice in 3 dimensions, I need 3 non-coplanar vectors. For instance, in this figure you can see these non-coplanar vectors as marked as A, B and C. There are 3 angles which can be considered. The angle between the A and the B, which is given by the gamma angle, which is actually opposite the C vector. It is a face which is opposed to the C vector. Similarly, you have the beta angle and the alpha angle, which go on to define a general parallelopipedon, a parallelepiped in 3 dimensions. Now these lattices are infinite in 3 dimensions, and we can, as usual, choose a unit cell which can be used to describe these lattices in 3 dimensions. These, as shown in this figure, we have 6 lattice parameters to describe a general lattice in 3 dimensions. These are 3 distances, A, B and C, and there are 3 angles, the alpha, the beta and the gamma. Now, as we go along to studying these lattices, we will see, as we did in 2 dimensions, there will always be special cases wherein some of the distances like A or B or C may be equal to each other, and there may be some of the angles which have some special values. Now, so this is, for instance, shown that you can actually have a 3-dimensional cube which is a space filling cube. To visualize a step-by-step construction, let us launch a small video. So let us start with a single cube and then go on to make a cubic lattice. The lattice points are at the vertices of the cube and have been left out from the construction for the sake of clarity. So first, starting with the cube, I make a layer of cells. Of course, this layer has to extend to infinity along 2 dimensions, and then I make the second layer, and on top of that I can make a third layer and going for to infinity in the direction which I am considering. You can clearly center of this figure, which has been darkened by the blue line. This exercise additionally shows the important point that cube is a space filling solid. So if I have such a lattice which is a cubic lattice, then the lattice parameters of the unit cell which goes on to describe this lattice will be A equal to B equal to C, and alpha is equal to beta is equal to gamma is 90 degrees. Again, to emphasize, this is actually a lattice. That means that it only conserves array of points at the corners of these or the vertices of this cube, and these lines are just for visualization and they have no physical meaning as far as this structure goes. And we have to also remember that these lattices would be infinite along the three directions, the x direction, the y direction and the z direction. Now, this was a very special case of a 3D lattice which I started off with. Let me now switch to the other extreme case wherein we have the most general possible 3D lattice, wherein I have no constraints on the alpha or the beta or the gamma, and A, B and C also happen to be independent parameters which can take values depending on the kind of lattice I am considering, the size of the lattice I am considering. Now, let us try to visualize how this lattice can be constructed, starting with the cubic lattice which I saw before, and additionally this exercise will show us that any general parallelepiped in 3 dimensions is actually a space-filling parallelepiped. This might seem obvious after the construction or from the figure which is drawn for you here, but unless this exercise is taken up at least for once, it sometimes is confusing when you see some general kind of parallelepiped and it makes you wonder, are they really space-filling? So let us start with the original cube which I had considered before. This is the cubic lattice with the cubic unit cell overlaid on the central one. I have the 3 directions. First, I start by dilating along the z direction. I pull this lattice along the z direction so that now the c lattice parameter becomes different from the other 2 lattice parameters. Further to this, I can perform additional operations like I contract the lattice along the other direction, which is so that now I have a squeezing operation which is taking place. I don't stop here, so I have done a dilation operation, then a squeezing operation. I go ahead and do a shear operation on this kind of a lattice. The shear operation is shown by the 2 shear vectors in the top and bottom, and you can see that this finishing lattice has been completely distorted with respect to the starting lattice, and none of the original directions or distances are equal, and also the angles have been distorted. So this is now a general parallelepiped, and it happens to be a space-filling parallelepiped. So we have now considered the important fact that any general parallelepiped can be a unit cell for a lattice in 3 dimensions, and that is a space-filling solid as well. Now, the lattices in 3 dimensions are called the Bravais lattices, and there are 14 of these. So let us try to read the matter written in the slide to understand what are these Bravais lattices. As usual, a lattice is a set of points constructed by translating a single point in discrete sets by a set of basis vectors. So there are 3 basis vectors in 3 dimensions, and we land up with 14 unique Bravais lattices. Distinct from each other, they have different space groups. We have not considered this concept of space groups in detail, but in this slide we try to have a broad overview, even though some of the concepts are beyond this elementary course. All crystalline materials recognized till now fit in one of these arrangements made by these 14 Bravais lattices. In geometry and crystallography, a Bravais lattice is an infinite set of points generated by a discrete set of translation operation. Like before, translation is the key operation when it comes to distinguishing lattices. An important property of the Bravais lattice is a Bravais lattice looks exactly the same no matter from which point in the lattice one views it. So that's an important property of lattices, and we will have a few more things to say about this important property of having identical surroundings and the view from any lattice point. Bravais had concluded that there are only 14 such possible lattices, and we use some conventional unit cells to represent these lattices as before. And an important point to be noted that these 14 Bravais lattices belong to the 7 crystal systems. Of course, we will have much more to say that how we go from lattices to crystals, and then how we classify these lattices into these 7 crystal systems. What do I mean when I say a crystal system? All these aspects we will consider in considerable detail when we actually start to build a lot of crystals using these lattices. An important point which might be noted is that there are 14 Bravais lattices which are space group symmetries of the lattices. So this again is an advanced concept, but just for the passing it is worthwhile to note this statement which is written in the end. So we are not showing the derivation of either of these 14 Bravais lattices, or we don't prove the existence of 7 crystal systems in this elementary course, but it is worthwhile to note these important numbers which will form the basis for quite a bit of the treatments we will be dealing with in this course. Once again, I have highlighted the important property of lattices and also the existence of 7 crystal systems and the 14 Bravais lattices. Further, let us consider a few more important points before we actually take the 3-dimensional lattices one by one. Lattices exist independent of our intentions to make crystals using them. So this has to be understood clearly. Yes, in crystallography, our idea is to use these lattices for making crystals, but their existence is a mathematical fact, and they do so without our intention to make crystals using them. The 14 Bravais lattices have 7 distinct symmetries, and this aspect that based on symmetry we can assign these 14 Bravais lattices to the 7 crystal systems. So there is a logical reason why do we have 7 crystal systems, and that is the symmetries of the 14 Bravais lattices. There are preferred unit cells to describe these lattices and crystals. The number of such unit cells is 7, which we use to describe these 7 crystal systems. However, we should again note that the shape of the unit cell should not be confused with the crystal system or the lattice. So this is an important point. We'll again return to it in various forms to understand this very point. So what are the 14 Bravais lattices? I have a question from Mr. Patel.
Sir, here the Bravais lattice and crystal systems, there are 14 and 7. These are fixed number or we can vary?
Okay, very, very good question I've got from Mr. Patel again here. First thing, the S is slightly silent in Bravais, so it has to be pronounced as Bravais lattices. In English, often we have a lot of words in which the last alphabet is pretty silent, like P-A-P-E-R is paper and not paper. The R has to be a little silent. So this is Bravais lattice. And to address your specific question, that are these numbers fixed? Yes, mathematically speaking, these 14 Bravais lattices exist independent of anything else. There is a mathematical construct. So as long as you impose the requirement that you have translation as a symmetry and every point has identical surroundings, then you will land up with 14 Bravais lattices. If you look at the symmetries of these Bravais lattices, you will see that there are 7 distinct symmetries. Now, there is still an independent question. Would you want to call these 7 symmetries as 7 crystal systems, or would I want to play some games further to it? We had seen in 2 dimensions that the crystals with 3-fold symmetry, of course we will come to this topic a little more detail later also, but we had briefly considered this aspect, that crystals with 3-fold symmetry and crystals with 6-fold symmetry both are put under the same umbrella, right? And they come under the 120-degree parallelogram crystal or the 120-degree rhombus crystal. Now, if you do not want to use 7 boxes to put and call 7 different crystal names, which some people do, some of the people actually put crystals in the hexagonal class and the trigonal class, which we will consider of course very soon. That means crystals having only one 3-fold axis or having one 6-fold axis under the same group. That means they do not classify them as separate classes. So in that, if you do such a kind of a classification, you will end up with only 6 crystal systems. But the preferred system is a 7 crystal system, because as you can logically see, because they come from the 14 Bravais lattices which exist independently, and if you look at the symmetries of these 14 Bravais lattices, there are only 7 distinct types which form the 7 crystal systems. So let us now try to divide these 14 Bravais lattices into the 7 crystal systems and also study some important properties of them. So we have an idea on the second column, which is a symmetry based concept, which is a crystal system. On the third column, we got the shape of the unit cell, which is wherein, as we saw, certain guidelines apply when we try to choose the shape of the unit cell. On the right hand side, we have the Bravais lattices, which is purely a translation based concept. Okay. So what are the Bravais lattices and how do we divide them into the 7 crystal systems? So the 7 crystal systems are the cubic, the tetragonal, the orthorhombic, the hexagonal, the trigonal, the monoclinic and the triclinic crystal systems. Now, sometimes a word crystal class is also used to describe the 32-point groups, and that terminology is confusing with when you talk about crystal systems, and therefore the word crystal classes is to be typically avoided when describing crystal structures. Now, of course, which is not very important at this stage, but just to, for instance, list some of the shapes of these typical unit cells. A cubic crystal is described by typically a cubic unit cell. A tetragonal crystal is described by a square prism of a general height. The orthorhombic again, which is of a general height. That means that height has to be different from any one of the other two lattice parameters in the plane. The hexagonal crystal is described by a 120-degree rhombic prism. The trigonal crystal is described by a parallelepiped, a special kind of parallelepiped which is equilateral and equiangular, which means every face is identical and every angle is identical. And we might also briefly see how we can go from a trigonal cubic crystal to a trigonal unit cell. The monoclinic crystal is described by a parallelogramic prism, and a triclinic crystal is described by a unit cell which is of the most general kind of a parallelepiped, wherein there are no special constraints either on the sides or on the angles. On the right hand side are the Bravais lattices. We shall of course take up each one of these Bravais lattices point by point. There are four types of Bravais lattices which are possible. The P, which stands for the primitive, I, which stands for the Innenzentrum in German, which is the body centered. So please remember, this is not from the English word, therefore I stands for body centered, F stands for face centered, and the alphabet C is used sometime as the side centered or the base centered, or sometimes it's also called the C centered lattice. Of course, the C centering need not be along only the C axis. You could have an A centering or the B centering, but as a class they form the C centered lattices. So if you look at this table, let us see that what kind of cubic lattices are possible. You can have the primitive cubic lattice, the body centered cubic lattice, and the face centered cubic lattice, but there is no C centered cubic lattice possible. Similarly, you can see in tetragonal class, you can have the primitive, the body centered, but there is no face centered or C centered cubic lattices in the list. In the hexagonal class, again you have certain things missing. In the trigonal class, the same I, F and C are missing. The monoclinic class, as you can see from the list, is the orthorhombic case, wherein you have the primitive, the body centered, the face centered, and the C centered lattice possible. So let us take up these 14 Bravais lattices as they are divided into the 7 crystal systems. We will return to this concept of a crystal system in little more detail. Therefore, if any confusion exists, would be clarified at a later point. So now we are basically trying to understand the lattices. One important question which comes to our mind when we consider these lattices is that why are some of the entries missing? It was very clear when you looked at this list. For instance, the hexagonal lattice, there was only one, the primitive, all the others were missing. So in the list there are many of these lattices which go missing, and like in the case of two-dimensional lattices, we can ask this question, why some of these lattices are missing. For instance, specifically, why there is no C-centered cubic lattice? Why the F-centered tetragonal lattice is missing? We will soon return to this question and answer with a few examples why some of these lattices go missing. So now, since there are 4 types of lattices possible, the primitive, the body centered, the F-centered or the face centered, and the C-centered lattice possible. Now let us look at the contribution each lattice point makes to a unit cell. Now in a primitive lattice, each lattice point at the corner contributes only an average of 1/8. Of course, depending on the shape of the lattice, these contributions may or may not be equal, as we have seen before, but typically you have 8 of them contributing a total of 1/8 on an average, giving rise to an 1 lattice contribution in the case of a primitive unit cell. Therefore, primitive automatically implies 1 lattice point per cell. In the case of the body centered lattice, the 8 as before give a contribution of 1, which are the ones located at the vertices of the lattice or the vertices of the unit cell. They give a contribution of 1. There is one which is completely included within the unit cell, which is giving a contribution of 1. Therefore, all body centered lattices have a contribution of 2 lattice points per cell. For the face centered, we will see that there are lattice points at the corners, and in addition there are lattice points at the center of each face. Of course, we will see examples to make this matter very clear, but there are lattice points at the centers of each face. Each face is shared between 2 unit cells, and therefore they have a contribution of halves. Since there are 6 faces, you have a contribution of 3 from the faces, 1 from the corners, making it a total of 4 lattice points per cell. In the case of the C-centered lattice, there are 1 contribution as usual coming from the corners. In addition, there is 2 half contributions coming from the opposite set of faces, making contribution of 2 to the unit cell. That means there are effectively 2 lattice points per cell in the case of a C-centered or A-centered or B-centered lattice. So let us now try to take up these lattices one by one in 3 dimensions and try to understand additionally using models that how we can understand these lattices. Okay. So let us start with the cubic lattice. As we saw in the cubic lattice, the shape of the unit cell is a cube as shown in the center. There are 3 kinds of centerings or additional lattice points possible. Only 2 of them are present, 1 is missing. So you have the primitive, the body centered and the face centered. No C centering is possible. And we also additionally can ask the question, why is this C centering not possible? Now, whenever we are showing such a figure, we will have a general figure in the middle which shows the basis vectors and the relationship between the angles of these basis vectors. We will also show this interrelationship between the lattice parameters explicitly at the bottom. In addition, we will also show the 3 lattices possible. An important point to note in these figures would be the symmetry, which is shown in the blue colored box. Now, this is a very important point to note because we said that these 14 Bravais lattices only 7 distinct kind of symmetries. That implies automatically that let it be a P lattice or a P cubic lattice or a body centered cubic or the face centered cubic, the symmetry of all of those kind of lattices will be the same, which will be according to the Hermann-Mogwan symbol 4 by m, 3 bar, 2 by m. So what I will do now is that let me show this is a cube on the left hand side in which only lattice points are present along the vertices. Like I told you, in the body centered case, you have lattice points in the corner, and in addition there is a lattice point at the center of the cell, and if you want to track the vertices of that or the coordinates of that lattice point, it will be half, 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 and such a lattice point will be lying along the body diagonal of the cube. So it will be half the distance of the body diagonal of the cube. Now, in the case of the face centered cubic lattice, you obviously have lattice points at the corners, and in addition you have lattice points at the centers of each face. So there are 6 faces, and at the center of each one of these faces you have a lattice point. And as we had pointed out in the previous slide, each one of these can only contribute half to the unit cell because such unit cell will be shared between 2 neighbors, and therefore this lattice point makes a contribution of half to this unit cell. Before I take up the case of the tetragonal lattices, let me try to illustrate whatever we have seen so far for the cubic lattice using some of the models I have got right with me here. And before I go to the models, Mr. Patel has got a question.
Sir, how we can understand the symmetry representation? This symmetry representation?
Okay, very good. So this symmetry representation, though we have dealt with in a little bit or in a brief manner in the very first chapter, maybe we can return to it later in the course, but this is basically what is called the Hermann-Mogwan symbol, and we saw that a cube actually has this symmetry. So maybe using a model I will briefly show how these symmetry elements are possible, but as you might remember, we had considered this in the early chapter on symmetry. Cut. So to answer Mr. Patel's question, I've got a model here of a cube, and using this I will show the symmetries of this cube, and for now I will have to assume that the points which are relevant are these lattice points at the corners which are in red color. So you can see the red colored points, and I wish to show the symmetries of this cube. Obviously this cube has a 4-fold symmetry which goes from the center of one face to the center of the other face. So this is my 4-fold axis, and as if you look at the Hermann-Mogwan symbol, I have got a symmetry of the cube as 4 by m, which I can write on the board. Now, the symbol 4 by m tells me that there is a mirror perpendicular to this fourfold axis, and actually the seat of the mirror is exactly halfway between the top face and the bottom face. Similarly, the cube would have a fourfold axis along any one of these directions joining the center of the opposite faces, and there would be a mirror which bisects these edges. So that is the 4 by m symmetry which is the cube having. It has an additional symmetry, the 3-bar symmetry, which you can see. A 3-bar symmetry implies a 3-fold roto inversion axis, which is actually an higher order operator as compared to the 3-fold axis. Yes, a cube also has a 3-fold symmetry along the body diagonal, as you can see. This is my body diagonal of the cube, and there is a 3-fold symmetry. But whenever I have a higher order symmetry, then I use that symmetry to describe the object and not the lower order symmetry. To give an example, let me consider a hexagon on the board. So for now we'll have to assume this is a regular hexagon, and this hexagon would have a 6-fold symmetry at the center. Needless to say, this hexagon also has a 2-fold symmetry and a 3-fold symmetry. But these symmetries are lower order symmetries as compared to the 6-fold symmetry, and therefore whenever a question is asked, what is the symmetry of this hexagon, I will report that the symmetry of this hexagon is 6-fold, and I will not use the lower order symmetries which happen to be subgroups of this 6-fold symmetry. Similarly, even though the cubic lattice or the shape of a cube has a 3-fold axis along the body diagonal, I will report the symmetry to be a 3-bar symmetry and not merely a 3-fold symmetry. Now, as we will see very soon, the very characteristic symmetry of a cubic crystal is this existence of this 3-fold along the body diagonal and not the existence of the 4-fold. The last symmetry which I need to consider in this symbol is the 2 by m symmetry. The 2-fold axis exists at the line joining the opposite edges. So the opposite edges are joined by a line, and that line is the direction of the 2-fold axis. You take any pair of edges, say this edge and this edge, and you have a 2-fold symmetry. How do I know I got a 2-fold symmetry? I can rotate it by 180 degrees and the cube will look exactly identical. It is similar to the existence of a 3-fold symmetry along the body diagonal, in which case I would rotate by 120 degrees to leave the shape invariant. Now, apart from this 2-fold, there is a mirror perpendicular to the 2-fold. So my 2-fold direction is this, which joins the opposite ends of the body diagonal, and the mirror bisects this 2 opposite faces as a diagonal. So I have a plane which passes through like this, the mirror plane, which actually bisects this line joining the 2 opposite edges. So I have a 2 by m symmetry, and therefore as a combined symmetry I can write the symmetry of this object as 4 by m, 3 bar, 2 by m, which is the characteristic symmetry of all cubic lattices. As we were discussing cubic lattices, I have with me some models here which I am going to use to explain the lattices which we just now saw on the computer. In between I have a question from Mr. Ravi.
So is there any 4-bar symmetry in cubic crystal?
Good question again. Can there be a 4-bar symmetry in cubic crystals? But yes, there can be 4-bar symmetry in cubic crystals, and we will actually consider examples of those crystals wherein 4-bar symmetry exists, but the higher symmetry in this case happens to be the 4-fold, and therefore we consider the higher symmetry to describe these lattices. And when we make crystals out of this, we will see that those crystals can actually have lower symmetry, and one of those possible symmetries is the 4-bar symmetry. So now let us focus on these 3 models I have got with me here. In this case, you will have to assume that these are actually not large blue spheres, but actually points, because now we are considering lattices, and therefore lattice consists only of points. So these, for my consideration, are points. Later on I will use the same models to describe crystals. At that point of time you will have to assume they are motifs, but for now they are lattice points. So I have a model of the simple cube on the left hand side. I have a model of the body centered cubic structure on the right hand side here, and behind those 2 models I have got the structure of a face centered cubic unit cell. So let me pick up one of them in the hand, the simple cubic unit cell. As I can clearly see that this has got 8 points at its vertices. Each one of these points is now shared between 8 such cubes. One cube of course is this one. There will be a cube to its right which will also share this lattice point. There will be a cube above it which will share a lattice point. there will be a cube on this quadrant which will also share this lattice point, and correspondingly there will be 4 cubes behind it, 1, 2, 3 and 4, which will share this lattice point. Effectively this sphere is being shared by the 1/8 of each one of these lattices, and therefore effectively the contribution to this lattice is just 1. So this is my simple cubic unit cell, which is the unit cell of the cubic lattices. Now let me pick up the body centered cubic lattice. Again, I have to assume that these are not spheres and these are merely points. Now if I look at the unit cell now, the unit cell is a cube as before, because all the edges of the cube are marked in red. These additional points have to be ignored, because these additional lines or strands have to be ignored, because they are just merely there in place to hold the central position in place, and they are not meant as to be any descriptors of this unit cell. So unit cell itself is made of these red strands. Now as you can clearly see, these 8 points contribute 1/8 to the cell, totally making a 1 lattice point. In addition, there is one in the center which is completely contained within the unit cell, and that has a contribution of 1 to this unit cell, and therefore it has a contribution of total 2 lattice points per cell. Now as I pointed out when I mentioned the videos, that this lattice point bisects the body diagonal. What is the body diagonal of the cube? The body diagonal of the cube is the one which is connecting this bottom sphere to the top sphere, which is along the 3-fold axis of the cube, or if you want to use the correct terminology, 3 bar axis of the cube, and this body diagonal is bisected by this point in the middle. Now how many of such body diagonals are there in this cube? It is obvious from this. There are 1, 2, 3, 4 body diagonals within this cube, and each one of those 4 body diagonals is bisected by the central point, which is the position half, half, half in the cube. Now let us take up the next model, the model of the face-centered cubic lattice. Now as usual, we have points in the corners, the 8 points. In addition, every face center has a point in the middle. As before, I should only focus, as far as the unit cell goes, on the red strands and not on these other metallic strands, because those are there just to hold the balls in place and not to describe the unit cell or the structure. Now the contribution, as I pointed out, from these opposite face walls is just half to the unit cell. As you can see, only half of this lies within the unit cell, other half is on the unit cell on the right, and therefore have a contribution of 3. These opposite pair contributes 1, and there are 6 such pairs, therefore you got the contribution of 3, 1 from the corners, 4 lattice points per cell. Now this lattice point bisects the face diagonal, which is the 1, 1, 0 direction of the cube, and therefore all the face diagonals are bisected by this lattice point. Now an important point to note, either for this kind of a lattice or for the body centered cubic lattice, is the existence of identical surroundings. When I say existence of identical surroundings, I mean if I am sitting at this lattice point or I am sitting at this lattice point, space should look exactly identical to me. If I am sitting at this lattice point, I traverse along the x direction by a distance half, traverse my x direction along half, z direction half, I would come to another lattice point. If I do the same exercise, half, 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 I land up another lattice point, and which clearly shows that every lattice point has an identical surrounding. The same visualization sometimes is little more difficult for the cubic lattice, but we should nevertheless try to do the same. And in this case, what is my shortest lattice translation vector? My shortest lattice translation vector in this case is not the cube edge. It is actually this vector which joins the 0, 0, 0 position to the half, half, 0 position. So this is my shortest lattice translation vector, which I can show by this red arrow here. So this is my shortest lattice translation vector, and if I use Miller registers to describe this vector, it will be an half, half, 0 vector. Now, or the half 1, 1, 0 vector as it's conventionally written. Now, as I was pointing out, each lattice has an identical surrounding. That means if I start from, for instance, this point, travel along the x direction half, travel the y direction half, I land up at a lattice point. Let me do the same exercise and let me see what happens. So I travel half, half, I land up at another lattice point. Similarly, I can locate longer and longer translations to locate different kind of, suppose I want to land up at this lattice point, I can go x half, y half, z1. If I do the same operation, again I land up at another lattice point. So even though the way I am representing this cube, the way this cube has been drawn, it seems to me that these lattice points are somehow looking different from these lattice points. It is not the case. Every lattice point is exactly identical. I could have chosen my origin here and the unit cell will look like this. I could have chosen my origin at this half of 0 point and my origin again would look exactly identical. So we have seen that there are three distinct cubic lattices, the primitive, the body centered and the face centered. Let us now go down to certain lattices with slightly lower symmetry like the tetragonal lattice. The typical unit cell, as you can see, which is used to describe these tetragonal lattices, is a square prism. That means there is a base which is square and it's a prism in the z direction. If I want to write down the lattice parameters for such a unit cell, it will be A equal to B, which is not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. Therefore, it is an orthogonal system. If you look at the lattices which are possible for the tetragonal system, they are the primitive lattice and the body centered tetragonal lattice. The face centered and the C centered lattices are not there in the listing. As before, the primitive lattice means there are only lattice points at the corners of the cell, and when I am talking about a body centered tetragonal lattice, there is one point at a distance half half half, which is the body centering position. As before, to qualify for a lattice, every lattice point should have identical surrounding, which is what is true for this kind of a body centered lattice as well. Now, the symmetry of these tetragonal lattices happens to be 4 by m, 2 by m, 2 by m. Now, all the tetragonal lattices, that means both the ones shown here, the primitive and the body centered tetragonal lattice, should have the symmetry 4 by m, 2 by m, 2 by m symmetry. Now, you can clearly see that the 3 in the second place is missing, and that is important to note. Additionally, we saw in the case of a cubic lattice, that the three orthogonal faces, you could, along the xy z direction, you could actually have a fourfold axis like here. I could draw a fourfold axis starting from this and going upward, a fourfold axis which connects the centers of these two opposite faces, and one along the y direction. You can clearly see there is only one fourfold axis in the case of the tetragonal lattice, and that fourfold axis happens to be along the c direction. You can draw the fourfold direction starting from the center of this face to the center of the top face. So the symmetry of all these tetragonal lattices is 4 by m, 2 by m, 2 by m. So where are these mirrors? The mirrors are the ones, as before, bisecting the body into two. So for instance, fourfold will be along this direction and the mirror would be bisecting this face. Now, corresponding to the mirror, which is this mirror, you can have a twofold axis which goes in the what you might call the y direction, which is along the b direction. So the b direction is a direction of twofold, the a direction is a direction of twofold, and only the c direction has fourfold symmetry in the case of the lattice or the unit cell which has been shown here. We can now consider even lower symmetry crystals, or sorry, lattices, and in this case the third lower in the list is the orthorhombic lattice. The unit cell used to describe such a lattice is the rectangular prism, and this rectangular prism means you got a rectangle which has been allowed to grow in the third dimension and therefore grows to be an orthorhombic unit cell. The one typical convention used when you describe these kind of unit cells is that A is chosen to be smaller than B, which is chosen to be smaller than C. But there are other conventions which are also possible, but there is no great sanctity as far as the symmetry or of the lattice in this choice of the order of the lattice parameters lengths. But however, certain conventions always help in communication across crystallographers and material scientists working in the area. What are the kind of lattices possible in the orthorhombic case? All possible lattices are there: the primitive, the body centered, the face centered, and the C centered lattices are possible. And as you can see from the figure, there is no relation between the A and B and C lattice parameter. However, all the angles have been constrained to be 90 degrees. As in the case of the cubic lattice, the primitive lattice has only points in the corners. The body-centered orthorhombic lattice has one additional point in the center. The face-centered orthorhombic lattice has points in all the corners and additionally at the center of each face. As before, these lattice points make a contribution of half to the unit cell, while the ones in the corner make a contribution of 1/8 to the unit cell. There is an additional lattice possible for the orthorhombic case, which is the C-centered lattice, and there could be cases where instead of the centering being along the C direction, you can choose a centering along the B direction or the A direction, and these additional lattice points only contribute half to the unit cell. So this is the C-centered orthorhombic lattice, which is an addition to the previous list as far as the cubic and the tetragonal lattices go. In the tetragonal lattice, we saw that the lattice has got a four-fold symmetry, and therefore we had a symmetry of 4/m, because you can see clearly these 4 points are related by a four-fold symmetry. Now these 4 points are not related by a four-fold symmetry, and therefore you got a symmetry of the orthorhombic lattices as being 2/m, 2/m, 2/m. That means each one of these directions would be a two-fold axis, and the mirror is perpendicular to it. So let me go down to the board and draw such a lattice just for the sake of convenience and see how we can get the 2/m symmetry. So this is my, for instance, a general orthorhombic unit cell. Of course, I am not constraining the A's and B's as shown in the diagram, but I am just considering a random orthorhombic lattice. Okay. So now this is my direction of the two-fold, for instance, which I show by the symbol, which connects the opposite faces. Now, the mirror plane in this case, as before, so this is my, to combine symmetry of these two operators, I write as 2/m symmetry. Now, similarly, this direction is also a direction of two-fold. And the third direction also has a two-fold. Correspondingly, there are mirrors which connect these faces as well. And to avoid drawing too many mirrors, I'll just draw 2 of them. You can see that there are mirrors which are perpendicular to these 3 two-fold directions. Therefore, I got a two-fold axis and a mirror perpendicular to it. This two-fold axis has this mirror perpendicular to it. I'll just outline this mirror in red direction so that I know that this is the one which is perpendicular to the two-fold. So I've got 3 2/m symmetry. So let me return to the slides. So now orthorhombic lattices have 2/m symmetry, and as we shall see later, that some of the crystals which belong to the orthorhombic crystal class can have a lower symmetry. The next lattice we consider is the hexagonal lattice, and as the name suggests, the hexagonal lattice has got a 6-fold symmetry. Now, the only kind of hexagonal lattice possible is the primitive hexagonal lattice. The body-centered, the face-centered, and the C-centered hexagonal lattices are not possible. If you look at the unit cell of a hexagonal lattice, it is actually a 120-degree rhombic prism. It is the prism which is drawn in the blue color. Now, often you would see representations in textbooks wherein you would actually see an hexagonal cell being drawn. It is to be absolutely clear, this is actually a combination of 3 cells. It is a composite of 3 cells and not a single unit cell for the hexagonal system. Now, the reason for drawing 3 unit cells is obvious. It is so that we can actually visualize the hexagonal symmetry which is present in these lattices. The basis vectors for such a unit cell are A, B and C. The angle between A and B is constrained to be 120 degrees. If it were not constrained, then this lattice would not have this hexagonal symmetry. The angle between A and C, and similarly the angle between B and C is 90 degrees. So we can have the relationship between among the lattice parameters as A equal to B is not equal to C, alpha is equal to beta is equal to 90 degrees, the alpha and beta being the angles between the A and C and the B and C axes, and the gamma, which is the angle between A and B, is equal to 120 degrees. The hexagonal lattices have a symmetry of 6 by m, 2 by m, 2 by m symmetry. Now, what we shall do before we go too deep into these hexagonal lattices, we would like to actually see a model of this hexagonal lattice and try to understand this lattice in a little more detail. And the model we have got here is again a combination of 3 unit cells, and we again will delineate a single unit cell within these 3 unit cells. To understand the concepts we were just talking about, the existence of an hexagonal lattice, I have a model here in front of me which I will use to illustrate the hexagonal lattice and also the unit cell of the hexagonal lattice. But before that, I have a question from Mr. Patel.
Yes. We know that here I, F and C points are absent, but if we are determined to know what will be the symmetry points if we locate some points.
A very good question. So Mr. Patel is asking, I know for sure that this, given the fact that I have listed only a simple hexagonal lattice, what happens if I actually enforce by putting centerings? For instance, I could put a C centering, I can put a center at each one of these faces, a lattice point, and I can have an F centering, or I can do a body centering to this kind of a lattice. What would happen? This is precisely the kind of questions we will ask in the coming slides, and we will answer that how these lattices, so all these other possibilities are not available. So we will precisely take up this very question. We will do the hypothetical experiment which I am precisely suggesting in the coming slides, and we will answer that such other additional lattices do not exist. So very good question, and we will be taking it very soon. So let us look at this lattice, and as before, you will have to assume that these are merely points and this is a lattice. Therefore, there is no motive to decorate this lattice. The typical unit cell is the one which is shown in red color. You can see here, and if you look from the top, you can clearly see that this unit cell has got, this structure has got hexagonal symmetry, the 6-fold symmetry. As before, I think there is one additional red which has been marked here, but please ignore this 2 reds at the top and bottom because they are not part of the unit cell. The only reds which need to be considered are the ones which are this rhombus shape and the one at the bottom which are rhombus shaped. Therefore, this is a composite of 3 unit cells, and this unit cell cannot be taken to this unit cell, which would be another rhombus, by merely a translation, and therefore there are, I would use the word composite and not a alternate unit cell or a parallel unit cell. So if I use this unit cell to describe this lattice, then I cannot use this unit cell or this unit cell to describe this lattice. However, this unit cell is related to this unit cell by a rotational symmetry of the hexagonal lattice. Now let me take up this model in my hand and try to understand it from various perspectives. So we saw that this has got a 6-fold symmetry which is obvious along the C direction. Now it has also got a mirror perpendicular to the C direction, which is the mirror which passes through the center of this body along the C direction. So I can put a plane which is a mirror which is going exactly between the top and the bottom planes. Now in some terminology, this is sometimes called the basal plane. These planes are called the basal planes, okay? And these are called the prism planes, and some inclined planes are called the pyramidal planes. Now the other symmetry which is worthwhile to note is the 2-fold symmetry, and you can notice that this structure between its opposite edges has got a 2-fold symmetry, and therefore if I rotate it by 180 degrees, you have a 2-fold rotation axis, okay? And additionally, I can pass a mirror which is perpendicular to this 2-fold, and the mirror would pass, as you can see from this side, would pass like this. So if I have a sheet of paper, then I can show you, and Mr. Ravi will help me with a sheet of paper to show you where is that plane. So I got a sheet of paper here, and you can see that the plane which is passing through this central plane is actually the mirror plane. And this sheet shows you that this mirror plane is perpendicular to this 2-fold axis. Therefore, this structure has got a 6 by m, 2 by m, 2 by m symmetry. one question we can ask is that how is this hexagonal structure related to some a common crystal which we come across, the hexagonal close packed crystal, and this we shall answer in due course of time. So again, to repeat the important salient features regarding the hexagonal lattice, this whole hexagonal structure is not a unit cell, though it could still classify as a cell for the structure. The conventional cell is this one marked in this red, which is nothing but a rhombic prism.